Okay, yeah, I would like to thank the organizers for inviting me to give a talk at this conference. So my talk will be based on a recent paper done together with one for one, and it will be about kind of incorporating different symmetries in a functorial way in some sort of in a way where we have a purely cohomological description, which is a bit different from what has been ordinarily considered before. So let me start, since there are kind of audience with audience with different backgrounds. Let me start by kind of briefly reminding you what is the notion of functorial quantum field theory. It's basically due to CR. So it can be defined as a symmetric monoidal tree of bordisms, the particular vector spaces. And so in my talk, I will assume that the vector spaces are all complex numbers, but everything can be done over algebraically closed field. In what forms. So, so what is this bordism category? Let me remind you. So, well, this category is bordism category. Manifolds. And usually we assume with a kind of fixed structure, given structure. And so by default, not explicitly specified as by default, the structure is just orientation manifolds and the smooth structure. But in principle, we can add, or I mean, you can also remove orientation if you want to. You can remove smoothness, but usually people add something like spin structure, and or we can even add something like Riemannian metric, and this will be kind of generic, non-topological quantum field series. While what we consider by default is just orientation smooth structure is what is gives us a standard definition of functorial topological quantum field theory. Okay, and so in this category objects, d minus one dimensional manifolds closed, and d-dimensional. So let's say these manifolds sigma with some index of isms. Let's say sigma minus to sigma plus bordisms. Isms that is different graph definition. So D manifolds such that there is a choice of isomorphism is a boundary with the disjoint union of sigma minus with reverse orientation sigma plus. And so here there's choice of isomorphism. One can imagine physically described from a space-time which propagates kind of spatial slices plus. And of course, whenever we have this choice of structure, this structure should the structures of the boundary should agree with the structure. Okay, and we want to consider it up to equivalence relation. So M is equivalent to M prime. If isomorphism such that it's basically identical to the bottom. Kind of diffeomorphism which doesn't change boundary. And of course, if you have additional structure, this kind of the pullback of the structure here should be given. The structure here should be given by pullback structure. Okay, and well, we're also talking about kind of as a functor means that in this sense you have objects and objects, and physically this the resulting vector space has a meaning of our quantum Hilbert space, the vector space of our quantum states given the -1 dimensional manifold. And okay, so we're also talking about symmetric monoidal functor. So it's a functor which preserves symmetric monoidal structure, and this is roughly the notion of tensor product. So on the bordism category, on the tensor product, it's a union, and then the product is empty manifold. And again, this is a so this kind of this functor is symmetric monoidal, which sends the disjoint union to tensor product of vector spaces, and these physically correspond to considering Hilbert spaces of decoupled systems. Okay. So when we talk about if you can take this M to be closed itself, here it has a bordism from empty manifold to empty manifold. So it will be map. So empty manifold. So the monoidal unit here is just a copy of C. So it's if you give it a map from C to C, which can then sort of the complex number itself, and this is what in physics called partition function. Okay, now we want to introduce symmetries. And first, let me first define using an execution function. No. Usual zero functions. You can see these G. So when I talk about symmetries, in my case, it would be non-anomalies. Meaning the symmetry is global. This means they're not Hooft anomalies, which means we can gauge it, and this is what we will want to do. So first consider the case of global symmetry is the following. So we call a closed addition function. This is called the ground. And okay, for my talk, I will assume the symmetry G. So in physics, when we talk about symmetry group, we actually need to fix the topology on this group, and I will assume this is a discrete topology. At the moment, the G doesn't need to be finite group, but later when we get to the gauging, we'll assume that's finite. So yeah, the partition function can depend on the choice of ground of the fish, so we can kind of a function of M background gauge field B. So what is this notion of background gauge field B mathematically? So there are different ways, equivalent ways to describe it. Well, and maybe the most classical way is to understand this B as a choice of principal bundle M, and we usually require some gauge invariance. This means that we consider it up to isomorphism. Another approach is to understand this B, a choice of B as a choice of a map from M to a classifying space of G, which when G is discrete is the same as the first Einbeck-MacLane space. And here we're considering up to homotopy. Yet another choice of description is to understand B kind of as an element of from the fundamental group of M G up to conjugation. This kind of describes the set which describes all the polynomials in our gauge bundle. And when G is abelian, this can be also understood as the first cohomology group of M G. And yet another way to understand this B is this as a way which actually can be generalized to these what is called non-invertible symmetries. It's a network of d-1 dimensional acts of physics that have meaning of charge operators. Labolet elements of G, and so they should so it basically looks something like locally like d-1 dimensional manifold, but they can have junctions, and the junctions, the labels of junctions should agree with the group of nation effects. Something else. Here again, we have to use some sort of equivalence relation where we quotient on central moves roughly relate networks which locally influence. Okay. Yes. Yes. So equivalence here is basically by this is like how it's defined, the classifying space of bundles. The equivalence here is this representability of the first homology groups. This is the same, and equivalence from here to here, you basically use this can be understood as cycles with G coefficients, and this is the relation is Poincare-Edwards. You mean this? Yeah. Well, you want to. Yeah, one can build. No, in principle, H1 can be defined. I mean, one can build there is notion of Poincare-Edwards. I mean, in this particular case. Okay, when we go to P minus P from symmetry, there's this can be generalized to Okay, and also let me mention this. Okay, this is for global symmetry, and we can consider gauge symmetry. And the partition function on closed manifolds have to give by sum of all these choices of B. So I put it in quotation mark because one has structure defined. That's exactly what the sum means. There is some normalization. Actually important. Okay, and so in the paper by Piotr Pustin, the authors promoted the notion of P-form symmetries. Now we take group G, and here for P greater than 0, we need to assume that the G is a union. We talk by Pustin about these P-form symmetries, and this is the relevant talk by Zucker. Okay, and we also assume that P here is an integer between these. There are some meaning can be given for outside of this range, but we're not going to do this. Okay, and so I don't want to talk about generalization of this approach, but I will talk about generalization of these three approaches. So okay, B here, this approach will basically replace standard complaint space is equals first standard complaint space. Here we replace homology group with P plus first group. Yeah, by default, here by default I'm talking about singular cohomology in some case, and here we just roughly speaking we replace the dimension of these defects minus T minus 2 set. Okay, and let me call it C. So and now, well, what about, so this is all for when M is closed, but now we want to consider extension of these to bordisms, so that we can define them mathematically manifold theory as a function of one category of bordisms, and we also want to consider this gauging operation starts with one function and produces a function. Yes. Yeah, here we can see the model of these moves. Up to moves is basically gives a homology class. Yes. And okay, let me mention that this third approach is important when we want to generalize to non-invertible. Even anomalies. This anomaly just modifies what one means. Some extra factors here. Okay. So A, C are kind of relatively well and no. Yeah. Approach A. So A is the main origin of this is So you can see the arbitrary kind of homotopy type here. This is a function of homotopy quantum field theory, which drive. And the gauging procedure in this approach was considered by the way. I'm not going to mention differences in the approach. C to define it TQFT as a functor. So one of the main references is works by, there's multiple works by Pavel. Well, when I talk about this kind of anomalous, non-anomalous invertible symmetry, my moves is basically, I can understand this as a chain, sorry, as a cycle, kind of usual singular homology cycle, and the moves are basically adding a bound. Yes. Yeah, I mean, yeah, if you, I mean, whatever does not change the homology class. Yes. And yeah, so and B will be this stuff. So what is the motivation? Why do we need something like this? We want right here we want, and this will give us a kind of explicit description. The other kind of motivation is that there is so once we kind of define appropriate category bordisms, we can use it in the what is called universal construction. So use and this is a kind of general method, kind of which allows us to promote environments of manifolds to TQFT. In this case, we might have some sort of invariance of manifolds labeled by the homology classes, and we can promote it to TQFT. Okay, let me remark this is not kind of a trivial question, because if one naively just takes like for manifold with this bordism, one just takes this cohomology class or this cohomology class relative to the boundary, one's going to fail. So the first step is to define appropriate. Yeah, so basically, physically, you can understand this question as how to properly define the partition function on manifolds with boundary, where we use field description as a cohomology class, so that it's consistent with kind of pattern in relations. The first step is to define appropriate bordism principle. So we'll call this bordism category. Manifolds. Right. another advantage here. So kind of for closed manifolds here, everything is explicitly like all the gauge equivalence information is already taken care of. So we already everything is quotient. Here we kind of have to like keep track of these equivalences. Okay, so we'll leave the objects pairs sigma b, where sigma as before is the t-1 dimensional. And we implicitly assume the choice of the following additional data. The choice p minus p minus the 2 skeleton. I remind you that the skeleton is basically a union of cells is in our cell decomposition. So cell decomposition can be some sort of triangulation or something CW complex structure. Here, it's kind of important that we don't need to know all cell decomposition information of sigma. We only need to know this part up to this dimension. And B here is element of the T plus first cohomology group of sigma relative to sigma minus this skeleton, these coefficients in J. And I will usually use the shorthand notation as follows. So we'll, by default, the coefficients will be in G, and I will use this notion sigma hat for a d-1 dimensional manifold. Hat means that I will remove a skeleton of this dimension from it. This is sigma minus. So maybe have some sort of low-dimensional examples one can keep in mind. Following, so let's say d equals 2 equals 0. So sigma can be something like x1, and one can always choose a cell decomposition with the skeleton. C case where sigma Riemann surface, and we can always exist a cell decomposition. And for now, cell decomposition where we have surface polygon function by person boundaries identified. This gives cell decomposition. This. I'm doing both cases actually. So first, let me consider case so p equals 1. This will be so d minus p minus 1 will be 0, and this will be the skeleton, which is the single point. And I can also consider. So no, there's, yeah. And also can I can also consider p equals 0 case, and the skeleton will be this. It can be 0.8. I'm allowed to, so this is kind of minimal choice, but I'm allowed to choose like this. It's fine. No problem. Well, for people there, actually, one can use the fact that we always consider this when we consider complement, right? And the complement will be just this interior of this two cell, and the two cell, as I said, cell can be always deformation reductive to some point. So this is actually same case as a choice of point. Or actually, so yeah, so in this dimension, something actually very simple. It's basically a choice of a point. But in pi dimensions, if the this yeah, we'll mention this later. This is related to this CGP TQFT construction. They basically use the choice of point, but it can be fit in this more general setup. Some questions. Okay, this is objects of physics. Physics will be clear and complete. It will be, let's say, morphism minus to some plus. So it's a pair where M is a usual bordism minus plus. It's manifold. This and the extra data V, the class in first the cohomology of M relative to dm hat. Dm hat means that we, again, this is I will write it explicitly once more. So it's a complement, it's a boundary minus the skeletons in the boundary. So we have here we have let's say sk minus skeleton here, which is sk plus. So we remove okay. And we need the condition that the restriction to the boundary is equal to b plus b minus. Restriction means the pullback with respect to inclusion. This group is consistent. The restrictions considers with this choices of group here. Okay. And of course we need to consider equivalence relation with before. Bordisms can be related by isomorphisms before, such that it's identical to the boundary. And of course, it's capital B, and the B is equal, must be equal to pullback. Okay, so so far this is some sort of just choice, but next the real part is to define the composition. Yes. Yes. So basically, suppose this is a case where like skeletons. So we can have something like this B line, like concretable B line like this, or we can have something like this. The point is that we don't want to kill either of them. We can keep, so for example, if we consider just without this part, we would this would kill these guys. And we could consider, for example, relative to the full boundary, we will kill these guys. We want to kill. It's kind of a skeleton, the minimal thing we can we should allow to them end on in order for this to work. Here, what I do is that compare the case when P is equals to. So we want to say what does it mean to compose pairs. Because the it's kind of manifold itself we compose and let me choose this kind of boundary to be sigma minus, this boundary sigma plus, and this intermediate as a small sigma. So a minus can be understood as a bordism from this to this, plus this. Here we compose these arrows, and now we need to define P. And to do this, one needs to perform some relatively simple and for exact sequence gymnastics. So we have, so first part, we can consider the following part of the migratory sequence relative mode group. So let's, by this capital sigma without index, I denote the union of all these three guys. Here, heart means I remove the skeleton from this. This and this part is topologically zero just because I'm using functoriality and some simple dimensional arguments and the equivalence between singular cohomology and cellular cohomology. One can show this. Right, this part. Okay, so this is a would be D minus using functoriality. This is the same as this. Okay, sorry, no, this part. Sorry. Yes, this part is not zero. This part is h p minus p minus 1 of skeleton inside sigma, and this is because this is only contains cells up to dimension d minus p minus 2. This is 0. So in particular, this means that this map will be objective, and so here let's take an element which is or here I can consider this direct sum of b minus and b plus, and here it's taken to the restriction of b minus to sigma minus restriction of b plus to sigma, and well, by definition it should be this object is kind of the same object for these two morphisms, so it should be 0. So this means I can find a preimage here, which I call B bar. So it's not yet the stuff which I need. And so the B which I need then can be obtained small. So this, because of this is 0, this map is injective, so it's unique element. And we can also consider this sequence of relative cohomology groups. So here we go to HP plus 1 out. And from this, we go to HP plus 1 of sigma out. And this again, one can show this is 0 because this is H d minus P minus 2 of sigma relative to the skeleton in sigma. And so since this contains all d minus p minus two-dimensional cells, this will be just 0. So in particular, this implies that this map is surjective. It will be important later when we gauge. And so we take this b bar along this map to this is what how we define. Well, we first go here. So there exists unique preimage, and then I go like this. Yes, so this map, yes, this is a pullback by respect to inclusion, yes. Yes, yeah. So we use this, I mean, the fact that these, yeah, we had the condition condition that this restriction of B plus is given, is fixed by this object here and object here. So here we have some sort of sigma, let's say B sigma. Yeah, actually object in this bordism group will decorated. Here we have like B minus, here we have B plus, and so we have a condition of B plus restricted to B plus minus restricted to the sigma is B sigma. B plus restricted to C minus is so B minus minus B minus. Yeah, I guess we can write it. Yeah, as this by restriction I mean pullbacks. then it's straightforward to check the decomposition. It's okay. Here, I just use the like two long exact sequence. One is my recurrent sequence, and the other long exact sequence for the triple of topological spaces. Yeah, then we can define TQFT. This setting we can define TQFT. Well, symmetry T symmetric. We make a couple of remarks. So remark one is that yeah, some special cases. So when first equals 0 is yeah, we can use cell decomposition. Sigma is a single d minus 1 cell statement that always exists. A single d minus cell in each connected component. Then the sigma minus skeleton is just a collection of points. So 1 point each. So in particular, this case when d equals 3, G is C mod 2Z is was this special case actually like using this property when there is just our additional structure is just a choice of a point in each connected component. This is a agreement and an agreement with the TQFT of Blanche, Constantina here, and Putrov. So they constructed, they started and wanted to promote some invariance of three manifolds defined using non-simple category of representation of some role quantum group. So first there was defined invariance of three manifolds, and they were labeled the cohomology classes. They promoted it, wanted to promote it to TQFT. Another special case minus P is different still, and then the one can always choose the skeleton itself to be a collection of these points, 1 point each component, and then so here this point is basically a point in the center of this d minus ones. And this somebody, yeah, case when d equals 3, z, this was considered an paper by Constantina. So And so here it was about relation of this Z cut invariance of three manifolds, which Sergey Gutov gave a talk about yesterday, and invariance it was actually given Putrov. Other remark is the following. So we have the following part of long exact sequence of homology groups associated with pair sigma hot. So we can go to E plus. Then next group quantum are related to 0 by the same type of argument as I showed before. And here we have HP. Which sigma we call this G and this and one can show that so kind of this skeleton is not supposed to be some physical information, so we want some sort of invariance on the change of the skeleton. I can make the following statement that we have isomorphism between two vector spaces. So here we choose sigma prime kind of as a copy of sigma, but with a skeleton sk prime, some possibly different skeleton inside. And we have then that this isomorphic if g of b is equal to g prime of b prime. This is equality in this group, which doesn't depend on the trading skeleton. But the information about which kind of we can get about forgetting this skeleton. And the isomorphism is just given by the value of one cylinder where it just different skeletons into boundaries. With something consistent choice of this group. Yeah. So the other part of the remark is the following: so this vector space forms representation of HP sigma, and so how does it work? Briefly speaking, so this rho B, the representation can be so the value again of the cylinder, where we have the same boundary conditions. That's why it defines the endomorphism vector space, and beta. So here we use there is a natural inclusion of this group inside the cohomology group associated with the cylinder. Here we have basically sigma, or and let's note two copies of sigma 1, sigma plus. This is related to sigma lines. Here and so here we define choice of cohomology class is 1.7. This is exactly subgroup. So this is exactly the image of the smoothly subgroup which preserves so if I use this notion for contracting dual groups on Z, then the representations, the reducible representations, they're classified by the contracting dual to this group. So it's where they write explicitly the coefficients, and this is known to be isomorphic to h minus p minus 1 of sigma, with now coefficients being the contracting dual. Okay. Now I can briefly formulate using what we have here, briefly formulate as a definition of the gauging procedure. Gauging operation. So as an input, we take our functor, or the output, the gauged, and so the functor from a different category, where instead of p, we have p star, which is d minus p minus 2, and g star is the contracting dual. And here, now I assume g is fine. Write a couple of formulas and stop. So objects, this operation defined as the follows: gauged, right? So this is a sigma with a dual d minus p star minus 2 skeleton. And a dual here means that so it must have the following property: complement the original skeleton, the deformation impacts to this. So in principle, yeah, I need to restrict to a category, to kind of subcategory where the skeletons have duals. So a particular example of this duality can arise if in one case I choose a triangulation, and in the other case I choose a dual polyhedron decomposition. But this can be more general. And then, of course, A is an element of H star plus 1, sigma hat star. This is can be defined as so. So maybe I will choose the right inverse as one of the smart G which we had before, which p plus 1 sigma See what people. And of course, it's right inverse only as for the sets, not as for the groups. So I will sum over and for the morphisms, are the following. So is that gauged? I take so here, yeah, I forgot to mention that we restrict to representation given by the analog of this map G is this for A element of this group. So G of A defines me element in each P star plus one sigma G star. And this is we saw that this exactly describes irreducible representations with respect to which we can decompose the space. Then we can consider this component is connected to a pair of B plus and B minus tilde in this sum. Some partition will be sum over basically as before. Here I need to here it's see. Here I introduce this factor exponent 2 pi I integral of B. And C of M factor given by the following product. Basically the sizes of cohomology groups and powers. Plus one. And so following theorem. So the first part is the following. So the formulas above to the left define a functor gauged. One can of course check that this well is consistent with compositions in particular, right? And is defined independently. So the various choices are made here. This dual skeleton, this choice of right inverse, but one can also argue that this is independent of choices of canonical natural isomorphism of concepts. And the second part is the following. If you start with some functor and we consider it's gauged, we apply this operation again. Let's get the original functor and so the result. So this is something which is kind of quite known in physics, but here I'm considering like precise formulation of the statement in terms of this functor on the category of bordisms decreased by cohomology factors. And the statement is formed. So we get essentially the original functor up to some corrections. So this C is basically involution functor, which takes which flips the sign of the cohomology classes. And this E is an invertible TQFT such that on manifolds, this is not TQFT not decorated by any cohomology class. On manifolds, D-manifold manifolds is just a copy as the vector space isomorphic to C, and on a closed manifold, D-dimensional manifold, the value of partition function is number of elements of G to the Euler characteristic. And well, the proof is essentially by calculation and some basic algebraic topology tools. I stop here. Sorry about that. So for this, no, it's just proportional to Euler characteristic. It's just Euler term. Yes. Here, this can be understood as some sort of Fourier transform product. Rate of symmetries, you get the same thing up to some factors and up to inverse of sign. Yeah, this is all included in this choice. In the choice of this original functor. This ambiguity is just tensor with the invertible TQFT. It's included here. Yes. Well, I mean, again, the discrete torsion modifies this original thing, and it will modify here. Yeah, here I choose just Gaussian basis. Yeah, this looks like Fourier transforms, and okay. Yes. So, well, my list was for the closed manifolds first, ABC. So there they are equivalent in. Yeah, they're all equivalent in both mathematically and physically. It's just when we quotient, yeah, there is some sort of basic series. And, but here, if you want to understand the relation between for bordisms, then one can argue that this choice of skeleton, like if you want to like a description in terms of this map to Eilenberg-Maclaurin space, the choice of skeleton is the choice of, we can see like maps of a very particular type. So basically constant outside of the skeleton, speaking. Yes, C is more geometric. C is nice because it can be generalized to this non-reversible symmetries. But the relation to C is just is basically concretuality. But here, when we use these cohomology groups, we already quotient our with respect to all the moves on the defects. So we don't really took defect. Yeah, the C contains a lot of more geometric data, but here we already quotient with respect to this equivalence. Sorry, yes, this plus is here. Thank you.